Welcome to the factory floor. I am Dr. Econ Master. When you look at an assembly line like this, churning out identical televisions by the thousands, the physical scale of production is clear. But our task is to determine how that physical scale dictates unit cost. Economists analyze this relationship through the concept of returns to scale. This measures what happens to total output when a firm increases all physical inputs, labor, machinery, and land, by the same proportion. Imagine doubling every single component of this factory at once. Intuition suggests a simple one-to-one relationship. If you double the workers and double the machines, you should get exactly double the televisions. Under this logic, the cost to produce each individual unit remains constant, regardless of how large the operation grows. This baseline scenario is called constant returns to scale. It describes a production environment where a proportional increase in inputs leads to an identical proportional increase in output. While this flat cost assumption is logically consistent, it struggles to explain the reality of modern markets. If scale provides no cost advantage, the dominance of massive multinational corporations over small local workshops becomes a mathematical mystery. To find the flaw in that logic, we must move from the factory floor to the whiteboard. We need to visualize exactly what constant costs look like in formal geometry. This chart displays the long-run average cost curve, LAC. Under constant returns, the red line is horizontal. We place U-shaped short-run average cost curves, SAC, along this baseline. Notice the geometry. The absolute lowest point of every short-run curve perfectly touches the long-run baseline. This perfect tangency implies cost neutrality. In a world of constant returns to scale, a startup and a conglomerate face the exact same unit cost. In this scenario, scale simply does not matter. This creates our central tension. If scale dictates market survival in the real world, then the LAC curve cannot remain flat. It must bend. Consider the condition of increasing returns to scale. This occurs when output grows faster than the inputs added. Doubling the factory might triple the number of televisions produced. This technological advantage forces the LAC curve to slope downward. As the firm's scale increases, the cost per unit falls, creating the condition we call economies of scale. We can examine how a firm behaves here by isolating a single factory size, represented by the curve SAC1. Point B represents the absolute minimum cost for this specific factory. At this point, the facility is running at its maximum technical efficiency. When targeting an output of Q1, the firm bypasses point B entirely. Instead, the optimal point of operation, where the SAC curve meets the long-run curve, occurs to the left at point A. This raises a difficult question. Why would a rational, profit-maximizing firm choose to operate a factory at point A, where costs are mathematically higher than its absolute minimum at point B? The answer lies in a long-term mathematical strategy that the short-run efficiency curves tend to obscure. To understand this choice, we must shift our perspective. In the long run, a firm selects from an infinite menu of possible factory sizes to find the absolute minimum cost for its target output. The objective is to produce the target output, Q1, at the lowest overall cost possible, regardless of whether a specific factory is being used efficiently. Consider two ways to produce Q1. The firm could build a small factory that hits its minimum exactly at Q1, or it could build a larger factory and underutilize it. The geometry shows that the larger factory's cost curve actually sits lower at the Q1 mark than the very bottom of the smaller factory's curve. Because overall long-run costs are falling so sharply due to economies of scale, the sheer advantage of a larger facility outweighs the penalty of underutilization. The long-run curve envelops the short-run options from below. This creates a formal rule. A downward-sloping LAC curve always pulls the optimal tangency point to the left of the short-run minimum. In practice, the firm builds a facility that is technically too large for its current target, knowing that the structural advantages of scale make it the cheaper option. Under economies of scale, operating an oversized factory below its peak efficiency is the most effective way to minimize long-run costs. We can test this logic by reversing the scenario. Suppose a firm grows so massive that bureaucratic overhead and logistical complexity begin to penalize production. This is decreasing returns to scale, where increasing inputs yields diminishing returns in total output. The long-run curve now flips. We have an upward-sloping LAC, known as diseconomies of scale. Focus on factory size SAC 0 and its absolute minimum efficiency point, marked as point E. Based on our previous logic, we can predict where the tangency point will fall for a target output of Q3. Because the LAC is pulling upward, the tangency point F is forced to the right of the minimum point E. To avoid the massive costs of building an even larger, more bloated factory, the firm chooses a smaller facility and overworks it past its optimal capacity. The envelope theorem remains consistent. A downward LAC pulls tangency left, favoring an underutilized large plant. An upward LAC pulls tangency right, favoring an overutilized small plant. These combined scenarios suggest a symmetrical U-shaped long-run average cost curve, where firms eventually become too bloated to remain efficient. However, we must ask if modern corporations actually experience this theoretical upward curve. Does growth eventually reach a mathematical ceiling? Real-world data contradicts the U-shaped model. Instead, we see an L shape. The L curve shows sharp cost drops initially due to economies of scale, but rather than curving upward into a penalty phase, the curve flatlines. This horizontal tail shows that firms can maintain constant returns to scale over vast ranges of output, effectively evading the bloat penalty. Because these giants rarely hit a threshold where they become too big to function, they can scale almost indefinitely without seeing their unit costs rise. Modern giants like Amazon or Samsung capitalize on the L curve by aggressively diversifying their output alongside their massive scale. This introduces economies of scope. This is the cost advantage gained by producing multiple different goods together using shared infrastructure, rather than producing them separately. A modern giant layers these advantages. It uses an L-shaped LAC to grow without penalty, while simultaneously using economies of scope to lower costs across a wide variety of products. This leads to a difficult question for the modern economy. In a market dominated by incumbents with these compounding mathematical advantages, how can a single product startup ever hope to compete on cost? I will leave that for you to debate in the comments. I am Dr. Econ Master. Always look for the reality behind the theoretical curves.